How many of you have ever walked on one of those moving walkways at the airport? You know what I'm talking about?
Yeah.
Those moving walkways that take you partway down towards your gate, save you a little bit of bother. Maybe you're carrying your suitcases and it's heavy and you get a bit of a break. Let's say that we've got a moving walkway that's traveling to the right at 3.0 meters per second. It's moving to the right at 3.0 meters per second. Now, let's say I get on that moving walkway. I get on that moving walkway, and I don't stand still, but rather I walk on the moving walkway. I'm in a bit of a hurry, so I walk at 2 meters per second on that moving walkway. Assuming that I walk in the correct direction, in the direction that the walkway is moving, then what's my resultant velocity? What's my velocity relative to maybe a store, a convenience store that's right there beside the moving walkway that sells pop and newspapers and potato chips and magazines? What's my velocity relative to that store? You've been on one of these walkways before, right? You know that if you're moving, you appear to be moving faster, right? And relative to that store over there, you are moving faster. Relative to that store over there, I'm moving at how fast? Not 2, 5 meters per second, right? My relative velocity is 5 meters per second. Now, how did I get that? I added these together, right? I said 3.0 meters per second plus 2.0 meters per second gave me 5.0 meters per second. That was my relative velocity. Now, what if I get on that moving walkway, the moving walkway that's moving at 3.0 meters per second this way, and I'm a little bit bored. I've been in the terminal for an hour and a half already. I got another 2 hours before my flight takes off, and I decide I need to do something to entertain myself. So I decide to walk backwards on the moving walkway. Instead of going forwards at 2 meters per second, now I'm going to go backwards at 1 meter per second, or sorry, at 2 meters per second. Now, relative to this store over there that's beside the moving walkway, how fast am I moving? What is it? 1 meter per second. Now, how'd you figure that out, Luke? Yeah, really what you're doing is saying 3 meters per second plus negative 2 meters per second, right? You're not subtracting, you're adding vectors together, but you're adding a negative value there, which gives me 1.0 meters per second. So I end up moving, still move forward at 1 meters per second. But because I was walking backwards at 2, it's not as quick as I was going. Does that make sense? When you're finding a relative velocity, we add vectors together. Now, we found a relative velocity in the first one that's much like the adding that you did in elementary school. We found a relative velocity in the second one that's much like the adding that you did in junior high school when you had to take into account positives and negatives. What if you were on something that was moving, let's say an ice floe. I was reading a story in a paper here, it might have been yesterday actually, where this guy somewhere, I want to say it might have been Newfoundland, decided he wanted to pose for a picture on this ice floe, and it started floating away. What's it? Let's say the ice floe is moving at 5 meters per second one way, to the right. But let's say the guy on the ice floe starts moving at 3 meters per, actually, let's make this 4. The guy on the ice floe starts moving at 3 meters per second down. What's the velocity of this guy relative to the ground now? Well, just like when we wanted to find the velocity of this guy relative to the ground, we added vectors together. 3 plus 2 is 5. Just like when we wanted to find the velocity of this guy relative to the store, we added the vectors together. 3 plus negative 2 gives me 1. This time we want to find the relative velocity of this guy. We add these vectors together. But to add these vectors together, we have to draw a vector diagram because we're in 2 dimensions. So we're going to say 4 to the right plus 3 head to tail, right? Drawn head to tail, equals my resultant vector, or the sum of my velocities, will be my resultant velocity or my relative velocity. If you're taking an overhead camera shot of this guy on this ice floe, relative to the shore, relative to the ground, it's going to appear as if this guy is moving down to the right. The ice floe moves to the right, he moves down, it's going to appear as if he's moving down and to the right. Okay, now how do I find that value? We've done that so many times over the last several days. It's the square root of 4 squared plus 3 squared, happens to be 5. And theta is the inverse tan of 3 over 4. I'm not sure what that works out to be. That works out to be 37 degrees. Does that make sense? So when finding relative velocity, listen carefully. When finding relative velocity, if it's a nice easy problem like this one, we add vectors. If it's a little bit more complicated problem like this one, we still add vectors. If it's an even more complicated problem like this one, we still add vectors together. When analyzing relative motion, you add vectors. End of story. It's just the only difference between these three questions is how we did the addition. 2 plus 3 was equal to 5. 2 plus 3 was equal to 1. 3 plus 4 was equal to 5. It's still adding, it's just how we add it together. Now, we're going to do relative motion problems now over the next couple of days. Relative motion problems involving real life things. Not like add these vectors together, 6 plus 7 plus 2 plus whatever at 37 degrees north of west, but rather we're going to say maybe a pilot aims or heads to the north, but there's a wind blowing to the west. What's the velocity of the plane relative to the ground? Or the captain of a ship aims her ship directly north across the river, but there's a river current that's going to the east of 10 meters per second. What's the velocity of the boat relative to the shore? Does that make sense? We're going to do problems that we've just been looking at, except in word problems with more real life type things. Now, as we do that, you have to recognize how to draw the diagrams. Right? This is what we got to do. Draw a vector diagram. But how do you draw the diagrams? You have to know which variable is which arrow. Okay, listen carefully. We're going to break these down into two types of arrows. Solid line arrows and dotted line arrows. A solid line arrow or a solid line vector might be wind speed. If the wind is blowing at 20 kilometers to the east, then that's going to be a solid line vector. The airspeed, okay, of an airplane. You ever get into an airplane, read the back of the magazine? Air Canada at least has, in the back of their magazines, they have all these different airplanes that they fly, and it lists all these different specifications of the airplanes, including the airspeed, how fast they can travel in still air. Okay? The air is not, maybe 900 kilometers per hour. Doesn't mean they can't go faster if there's a tailwind or slower if there's a headwind, but in the absence of wind, how fast could they go? The airspeed. What else could be a solid line vector? It could be where I aim or where I head. I aim in a certain direction. I head in a certain direction. These are solid line vectors. These are all vectors that contribute to my motion versus my dotted line vectors. My dotted line vectors, which could be my relative velocity, or you could say my actual velocity, or the velocity relative to the ground, where I go or where I want to go. These aren't contributing to my motion. This is my motion. If it contributes to where I go, then it's a solid line. If it is where I go, then it's a dotted line. Does that make sense? We'll give you one example and then we'll wrap it up for the day here. Captain of a ship aims a ship due north at a speed of 10 meters per second. Okay, the captain of a ship aims his ship. Does the ship actually go north, or does this aiming of the ship just contribute to where the ship goes? That contributes. There could be other factors that also contribute to where the ship goes, right? This is one of them. That means that's going to be a solid line vector, right? So let's draw this as a solid line vector at 10 meters per second because it contributes to where the ship goes. Now, there's a current in the ocean to the west. Does the current in the ocean actually, is that where the ship actually goes? Or does that current in the ocean just contribute to where the ship goes? It contributes. So let's draw that head to tail, 2.0 meters per second to the west as a solid line vector because it's not where the ship goes, it contributes to the ship. Now, the ship's resultant velocity, that's where the ship goes. That's going to be, well, let's make that my dotted line vector, my resultant velocity. Okay, you guys know how to find that. Here, let me just clarify this a little bit here, okay? Let's make this 10 over here, just so you can see it a little bit better. You guys know how to find that resultant velocity. The relative velocity relative to the shore, r is going to be equal to the square root of 2 squared plus 10 squared, which when you do the Pythagorean theorem to 2 digits, actually works out to be 10. Theta is going to be the inverse tan function of 2 over 10. Let's figure that one out. Gives me a value of 11 degrees. And this would be 11 degrees west of north. So, think about this. Captain of a ship is aiming directly north, but there's a current going this way. Logically, of course, the ship is going to end up going over there somewhere, right? Does that make sense? A solid line vector contributes to the motion, as does this solid line vector contribute to the motion. Where do I actually go? Over here somewhere. Got it? Let me give you this one. How many people drive? How many people have their driver's license? Okay. How many people have ever experienced this driving? You guys are fairly young drivers, so you may not have, but there's a good chance you have. In Alberta, we get a lot of winds, okay, Chinook winds, blowing like crazy, sometimes like 80, 90, 100 kilometers per hour. You're driving on the highway, okay, you're driving straight north on the highway. You look at your steering wheel, and your steering wheel is turned like this. You ever notice that? You're aiming northwest. That's not where you go, but where you aim your steering wheel contributes to where you go. There's a wind blowing to the east, which contributes to where you go. Those would be solid line vector, and then where I'm actually going, which would be along the highway to the north, that would be my dotted line vector. Does that make sense? Okay, I'm going to give you 3 questions to do for homework, all relating to this. It's going to be worksheet number 8, questions 1 to 3. So you have 2 things for tomorrow. Worksheet number 8, questions 1 to 3. In addition to that, you have a quiz. Quiz number 8, or number 7, I should say. Quiz number 7. It's a 2D vector diagram question, but no funny angles. No funny angles. Thursday is going to be funny angles, yeah.